Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at our lesson for 8.2.1. We are now going to get into the second part of chapter 8, where we're going to focus on exponent rules. And this is a great opportunity for us to talk about scientific notation, which is a specific way of writing numbers that scientists came up with because, when you're dealing with stuff like astronomy, like space, and you're talking about planets or star systems or galaxies that are so far away from each other, it's really hard to identify the number of miles or kilometers or whatever unit of measurement you're using just standard notation, standard numbers, because of the number of zeros that you would have to have. And so they created this system for writing very large numbers, but using exponents and powers. And it works the same for, like, when you look under the microscope and you're talking about really, really small numbers as well that would have a lot of decimal places. It works just the same for that. So today we're going to get you started with exponents, understanding how exponents work. And then day 2 of this lesson goes into a little bit more detail about how scientific notation works. But I'm going to front load the scientific notation right here and now. So basically, scientific notation is a process for making very large or very small numbers easier to write. And so an example of scientific notation might look like something like this. Okay, so what does the C represent? Well, let me actually write a number in scientific notation here. If we took 2 times 10 to the third power, that would be another way of writing the number 2000. Okay, so why do we do it this way? Well, 10 to the third power is a relatively small number, so you're not really saving a whole lot of space or time by writing 2000 like this. But if I change that to 2 times 10 to the 30th power, then you would be talking about a very, very, very big number with a lot of zeros. We'll get more into that a little bit later. Okay, so let me actually change and color code that a little bit. So yeah, okay. So C times 10 to the nth power is the algebraic way of looking at a number that's been written in scientific notation instead of being written in standard form. Notice how the C is this first number right here, and there's 10, and the 10 gets raised to the nth power, and that n can be any integer. Okay, so there are certain rules that we have here. First of all, C, that first number that is being multiplied times your power of 10, has to be a number that is between 1 and 10. And when I say between, it can be 1, but it can't be 10. It's got to be a number that has 1 digit in the ones place. You're allowed to have decimal numbers and numbers go beyond it, but we definitely want to have that never be a number more than 10 and never be a number that is less than 1. Okay, it can't even be 10. It's got to be less than 10, but it can be equal to 1. Okay. And then the n is the exponent to the power of 10, and we always want that to be an integer. It can be positive or it can be negative, but we don't want it to be fractional exponents. That we'll get into something like that in chapter 10, how fractional exponents work. Right now, we're only going to focus with the whole numbers or their opposites, negative. So this could be 10 to the negative third as well, and that would be okay for scientific notation. Okay, so we will revisit this in day 2 of this lesson. We are not going to spend too much time with scientific notation today because we need to understand the basics of how powers work. All right, so earlier in this chapter, you worked with expressions for interest problems. Remember the compound interest problems that we just got tested on. You could rewrite them in simpler ways by using multiplication in place of repeated addition and by using exponents in place of repeated multiplication. That concept goes all the way back to, I think, chapter 3 of 7th grade when we were learning about Cecil on the tightrope. But we'll just stay with the present here. Rewriting expressions in different forms can be a powerful tool for simplifying expressions and seeing patterns. In this lesson, you will develop strategies for how to rewrite expressions using exponents. All right, so the first question for reflection. Is 3 to the 5th power the same as 3 times 5? Because that's a common mistake students make. I can't tell you the number of times I've seen someone say 3 to the 5th power is 15, but it's not. If you remember that 3 to the 5th power means you're taking the number 3 and you're repeatedly multiplying it 5 times, you would see that 3 to the 5th power is not 15, it's actually 243, because 3 times 3 is 9, times 3 is 27, 27 times 3 is 81, and 81 times 3 is 243. So no, these two are not the same. 3 times 5, going back to our days of studying Cecil on the tightrope, literally means you're taking the number 3 and adding it repeatedly 5 times. Or you could have said 5 3 times. It doesn't make any difference. But just keeping this consistent. This is repeatedly being multiplied times itself 3 times. This is being repeatedly added 5 times to give you 15 for an answer. Okay, so we are going to be focusing on exponent rules for the remainder of this chapter. So repeated multiplication shortened so that you can write it as a power instead of expanded out. All right, so exponents allow you to rewrite some multiplication problems in a simpler form. Some exponent expressions can also be simplified. Complete the table below on the resource page 8.2.1 or copy and complete it on your paper. I would just recommend you do this, but I will make sure if it's not already there that this resource page is on the Google Math page so that you could print it off if you chose to. But to me, I just think creating the table, by the time you set everything up and print it, you might as well just copy it down. Okay, so here's the first example. The original form is an expression that involves you multiplying a couple of powers together. Actually, let me do this so we don't get a little bit distracted there. If you were going to copy all this down, go ahead and pause it, back up a little bit. You can get everything copied in. Where's the one I like? Ooh, that one's good today. Okay. So you got this expression, 5 to the 2nd power, and this expression, 5 to the 5th power. Well, what do each one of those mean? Well, 5 to the 2nd power literally means 5 times 5. And 5 to the 5th power literally means 5 times 5 times 5 times 5 times 5. So if you were to multiply 5 squared times 5 to the 5th, you'd be multiplying 5 times 5 times 5 times 5 times 5 times 5 times 5. Well, how many times are you multiplying that 5 together? 7 times, right? So the simplified version of this expression would read 5 to the 7th power. Now, I want you to look at a connection between the original form of these powers being multiplied together and the simplified form of that power, and see if you notice a trend, because we're going to come up with a rule for what you're supposed to do whenever you multiply powers that have the same base. So, what do we have going on here? We've got 2 squared times 2 to the 4th. How would you expand out 2 squared? Write that here. How would you expand out 2 to the 4th? Write that here. And then go ahead and count up all the 2's that are being repeatedly multiplied together and write the simplified exponent form here. So 2 squared is 2 times 2, and 2 to the 4th is 2 times 2 times 2 times 2. So how many total 2's are being multiplied all the way across? That would be 6 of them, so that becomes 2 to the 6th power. Are you getting closer to a rule for what happens when you multiply 2 powers that have the same base? Remember, the 2 is the base, right? Did we say that already? Hold up for a second. I might have that written somewhere else. But still, the 2 is the base. The exponent is the number in the upper right-hand corner. So same base, 2 and 2, gets repeatedly multiplied 6 times. Let's do the 6th. All right, try it now. 3 to the 7th times 3 to the 2nd. Go ahead and predict, without expanding it out first into factored form, what your answer is going to be in simplified form. Then go ahead and expand it out and see if you got the correct answer. If you think it was going to be 3 to the 9th power, that's what it is, because you're going to take 3 to the 7th, 3 times 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 3 squared, 3 times 3. And when you multiply all of them together, you're multiplying 9 3s repeatedly. So that's 3 to the 9th power. It's the same thing work for variables, unknowns. These x's are the bases. 7 to the 3rd times 7 to the 5th. How many total? Let's say 7. X to the 3rd times x to the 5th. How many total x's are being multiplied straight across? That would be 8 of them. So the product of x to the 3rd and x to the 5th has to be x to the 8th. What happens when we start blending different variables together? How are we supposed to solve this problem? Well, let's expand it out and see what we can do. I think we can all agree that x to the 3rd times y to the 2nd is going to be x times x times x times y times y. And then x times y squared, or xy squared. You notice how there's no exponent for the x there? But there is a ninja 1. You just can't see it. Okay? Whenever you do not see an exponent for a power, it's always the number 1, no matter what. And that's where it's really nice to expand this out. And you can literally count. When you go for the shortcut, sometimes people are going to miss that 1 there, and they're going to say x to the 3rd, y to the 4th. But it's not x to the 3rd, because you got x times x times x times y times x times y times y. So in this case, you literally have 1, 2, 3, 4 different x's being multiplied together. Your x to the 3rd and your x to the 1st. And that's pretty clear. Y squared times y squared is going to be y times y and y times y. So our final here is x to the 4th, y to the 4th. So if you're ever struggling with the exponent rules, I cannot stress enough the benefit of expanding it out into a factored form and then counting, literally counting the number of x's and the number of y's being repeatedly multiplied, and choose that number as the exponent. Okay, what about a blend of numerical bases with variable bases? Well, same thing happens. This is kind of a duplicate of that. You've got your 7 to the 2nd power and your 7 to the 1st power, and you've got your x to the 3rd power and x to the 2nd power. So how many total 7s do you have there being multiplied together? There's one, no, wrong color. Must coordinate colors. 7 times 7, and then another 7 here, for a total of 3 7s. So that would be 7 to the 3rd power. And then how many x's are, no, yes. How many x's are being repeatedly multiplied? 1, 2, 3, 4, 5. So our final simplified exponent form would read 7 to the 3rd, x to the 5th. Now I want to point one thing out here. Notice how I am not using the multiplication symbols once we get to the simplified exponent form. That's because when we're dealing with multiplication and algebraic expressions, there isn't a need to put the multiplication symbol between the different parts that are being multiplied together. Here, we're just trying to show you that you've got 1, 2, 3, 4 different powers that we're multiplying together. But when you finally simplify it, you end up simplifying it similar to how this is written right here. Instead of saying x to the 3rd times y squared, you can just call it x to the 3rd y squared, and we know that's being multiplied in there. All right, and now the last situation here, where you're blending variables and numbers as far as your powers go, or as far as your bases go, but now you've got a couple of different numbers. So what do you do with those? Well, let's still expand them out. And let me color coordinate. You got your 2, there's right there, there's your 2. You got your 4 x's here and your 1 x there, so 1, 2, 3, 4, 5 total x's being multiplied in. You've got a 3 here, which is your 3 here, and you've got your y squared, which is your y times y. So when we put these all together, we want to put the numerical parts together. So we're going to put the 2 and the 3 together, and the x to the 5th power times y to the 2nd power. And I don't know what x times y is because I don't know the value for either x or y in these expressions. But I absolutely know the value of the 2 and the 3. So it is okay to multiply them together and get the answer of 6. So we would write that as a 6, but then go back to the exponent rules for the x base and the y base. So this becomes 6x to the 5th y squared. Okay, so remember, this is an example of a power. The base is the big number that's being repeatedly multiplied, and the 5 is the exponent that tells you how many times you're repeatedly going to multiply this number together. So it says here, work with your team to compare the bases and exponents of the original form to the base and exponent of the simplest. No, let me read that again. Work with your team, or think to yourself, to compare the bases and exponents of the original form to the base and exponent of the simplified exponent form. Write a statement to describe the relationship you see. Okay, so we're talking about here. Let's just look at this first example. What did you do with the bases when you went from 5 squared times 5 to the 5th to 5 to the 7th? And what did you do with the exponents? What always happens there? So I'll just give you a bit of a shortcut there. The base stays the same, and the exponent is the sum of the exponents in the original form before we multiplied everything together. So that brings us to our rule for how you multiply powers together. Okay? Now, this rule is specifically for when you're multiplying powers that have the same base. Come back over here. These are powers with the same base. These are powers with the same base. Those are powers with the same base. But when we were down here in the last example, the 2 and the 3 did not constitute the same base. So this rule is not going to apply if you have a problem that is like 2 to the 4th times, oh, I better not put an x there, that's going to confuse, times 3 to the 2nd. This rule that I'm about to give you will not apply to this situation. It only applies when you're doing something like this, or like this, or like this, or like that. Okay? So, when multiplying two powers, or multiple powers that have the same base, you are going to add the exponents, and you are going to keep the base. Okay? So, let's go back to this problem once again. 5 squared times 5 to the 5th power. The answer, because we expanded it out to be 5 times 5 times 5 times 5 times 5 times 5 times 5, we're never going to have 25 in here. You're not going to say this is 25 to the 7th power, which is the most common mistake that people make. I'm going to make this does not equal 25 to the 7th. Because this is not 7 25s being multiplied together. It's 7 5s, okay? So, there is rhymed reason, or is that the expression I'm looking for? There is a reason why we do this. And there is a reason why we keep the base, but it's based in the logic, no pun intended. The logic of what happens when you expand out powers. What does the exponent mean you're doing to the base? And when you multiply them together, you're just making it a bigger multiplication statement. So let's take a look at this. It says, visualize how you would expand 20 to the 12th power times 20 to the 51st power in your mind. What would this expression be simplified to as a simplified exponent expression, or in exponent form? Well, if you could picture 20 multiplied repeatedly 12 times here, and then another 51 times here, you would have the number 20 repeatedly multiplied 63 times. So 20 to the 12th power times 20 to the 51st power is going to be equal to 20 to the 63rd power. We're multiplying two powers with the same base, So we added the exponents, 12 plus 51 is 63, and we kept our base. Okay, so here's a stoplight problem. One study team rewrote their expression like this. They did 5 to the third times 5 to the fourth as 50 to the seventh. Is this correct? And your answer is absolutely not! Exclamation point, no. 10 to the third times 5 to the fourth is literally 10 times 10 times 10, so that part is 1,000. And 5 times 5 times 5 times 5 is 625. If you took the number 50 and you multiplied it repeatedly 7 times, let's see if I can even, 50 raised to the power of 7, yeah, that's like 781 billion, as opposed to, oops, stop it, as opposed to 625 times 1,000, which is 625,000. Okay, so we do not multiply those together. They are not the same base, so you're not going to keep the base. And we're certainly not going to ever multiply this base times that base and then add those together. This rule only applies when you have two powers that have the same base. Okay? Okay. Go ahead and write that down. Put in your exclamation points. It's very, very important for people to understand this. Oh no, my battery is going down. I'm going to pause and I'm going to plug in and I'll be back. And you won't even know I was gone. Okay, I'm back. We're plugged in. All right. Now, I can imagine this last statement that I'm making right here that says you never multiply bases being kind of confusing because you're thinking back to here. It's like, well, wait a minute. Did you multiply the 2 and the 3 together there? And I would say, yes. Yes, I did. But I didn't multiply the bases when they were still in exponent form to get 50, okay? You can multiply them together here when you've got them expanded out if you eventually want to put it into standard form. That's the 625,000, which is the product of those two powers, okay? And so that's basically what I was doing in the previous problem where you had the 2 times the 3. Well, it was 2 to the first and 3 to the first, and we might as well simplify that by making it 6 to the first power, okay? But we're not going to bother putting in our exponents. We're just going to multiply those together when we're simplifying the expression, okay? So different powers, if you want to evaluate those powers and simplify them and write them in their final numerical form, you are allowed to do that, and that would require you to multiply. All right, so when you multiply, the order of the factors does not matter. That means that you will get the same answer when multiplying 3 times 2 times 3 as you would if you multiplied 2 times 3 times 3. This rearranging of factors that are being multiplied together is what we refer to as commutative property of multiplication. And we've talked about that a lot. I bring this up quite a bit when we're doing work. It doesn't matter the order of numbers that you're multiplying together. You can rearrange the order to make it easier to do mental math. The same property applies for addition. But now we're looking at this saying, okay, does that work for division as well? And I don't know why this is coming up in this problem or in this unit, but might as well revisit the idea that commutative property works for multiplication because both, oops, I guess I'll do that. Both 2 times 10 and 10 times 2 equals 20. However, 2 divided by 10 is 2/10. And 10 divided by 2 is equal to 5. So the answer is that commutative property does not work for division, just like it didn't work for subtraction either. But when you're adding or multiplying, you can absolutely rearrange the order of the terms, or in this case, the factors, I should say, of what you're multiplying together. So we're going to apply that to help us with this situation here. In fact, we did it already here, and we didn't even talk about the fact that we were doing it. So write the expression 5 squared times x to the fourth times 5x in factored form. Explain how the commutative property of multiplication helps you simplify this expression to be 5 to the third times x to the fifth. Okay, so we start off, let's expand it out. 5 squared is 5 times 5, X. What did I do? Hold on for a second. My bad. Okay, love it when I make a mistake, but then I catch it before too long. All right, so if you took 5 squared times x to the 4th times 5 times x, that's what it says, but now I've expanded it. And then I'm going to rearrange the terms and put the 5's together, right? You got this 5, and this 5. Let's just put them all together. And then you got this x, this x, this x, this x, and this x, and put all of them together, and you end up with your 5 to the 3rd and x to the 5th. So you are allowed to rearrange the order of the factors and sort the bases into groups. That makes it easier to write it in its simplified exponent form. So let's go ahead and do that here. Let's take problem C, write this down, expand it out, group all the numbers together, the common bases together, and then rewrite it in its exponent form, simplified. All right, let's see how you did. Did you start off by expanding it out? Yes, I hope you did. Remember, the exponent tells you how many of these you need to rewrite. So 3 times w times w times w times 3 times w times w times 3 times w times 3. Well, let's take all the 3's. 1, 2, 3, 4 of them, and all of the x's. 1, 2, 3, 4, 5, 6. And let's rearrange them so they're all together. So we got a total of 4 3's and 6 w's repeatedly being multiplied. So we're going to write that expression in simplest form as 3 to the 4th, w to the 6th. All right, now this is going to prep you for scientific notation. This idea of what happens when you multiply a number times the power of 10. Okay, so we're kind of going in a slightly different direction, but this is going to get your head in the right space for the next part of the lesson when we're doing scientific notation. So multiplying a number by 10 changes the number in a special way. Simplify each expression below without using a calculator. And as you work, pay attention to how the number changes when you multiply it by powers of 10. All right, well, let's just talk about this a little bit. We used to talk about this a lot last year when we were doing percent increases, and we often worked with like 10% or dealing with the number 10 sometimes. Whenever you multiply a number times the power of 10, you move the decimal the same number of places as the number of zeros in the power of 10. And if you recall from our lesson that we had, or was it homework that we had in a previous lesson of chapter 8, where the exponent for your power of 10 tells you how many zeros there are. So when you multiply a number times 10, you either add a 0 to the end of the number, like if I said 4 times 10, you would just add a 0 to 4 and make it 40, right? But if I said 4.1 times 10, you wouldn't write that as 4.10 because that's the same thing as that. They're both 4.1. So really what you're doing here is instead of adding a 0, is you're really moving your decimal one place to the right. But you got to put a placeholder in there. So your decimal now goes here after it moved one place to the right. Okay, here 4.1 times 10 is going to be 41, and this one didn't require a placeholder because you had a digit there that you can move around, so that would be 41. So that's what we're going to do here, 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 and here. Is every time you multiply times the power of 10, whatever your exponent is, that's going to be the number of zeros in your power of 10, which therefore means that's how many places to the right you're going to move that number. So a lot of times we do it mentally. 9.23 times 10, well, what's 9 times 10? We know it's 90, right? So 9.23 is going to have to be 92.3, so you would just move it one place to the right. This is 100. 9 times 100 is 900, so this number is going to have to be somewhere around 900. And so it makes sense for it to move 2 places to the right to become 923. This number is 1,000. 10 to the third power is 1,000. It's got 3 zeros. So what is 9 times 1,000? It's 9,000. So it makes sense that we would have to move our decimal 3 places to the right but you're going to need a placeholder of a 0 there, so you can go 1, 2, 3. And then 9.23 times 10 to the fourth, it's going to have to move the decimal 4 places to the right. So 10 to the fourth is 10,000. 9 times 10,000 is 90,000. So your answer's got to be somewhere in the 90,000 range, and 92,300 is the correct answer. So when you're using the rule here, just remember, sometimes you can just move a number of places to the right. Other times you need to add some zeros so that you'll have enough places to get to the right where you need to get to. Okay? And I believe that, oh no, it's not. What time is it? Sheesh. I had no idea this was such a long lesson. All right, so let's do this really, really quickly. Based on the patterns, what do you think 9.23 times 10 to the 7th would be equal to? Well, you're going to have to move it 7 places to the right, correct? So it's going to be 92,300,000. Okay. Without using a calculator, copy these guys down, move the decimal the appropriate number of places to the right, and declare your answer. I'm going to go ahead and reveal it. Hopefully you paused and you figured it out on your own, but if you're just in the mode for copying me because it's getting really long, that's fine. So this is going to be 2 places to the right, so it's going to be 7,865.9. It says to move 5 places to the right, so you're going to have to add some zeros there. Zeros there, there we go, and then put your commas in because remember every 3 digits from the decimal point gives you your grouping. This is the ones grouping, the thousands grouping, this is the millions grouping. So it's 34,638,000, and that's where we end it. Okay, so your team, write a statement. Now I'm just going to let you copy this down. Each time a number is multiplied by a power of 10, the decimal moves a place to the right. So 78.659 times 10 to the second literally means you're multiplying it times 10 and then times 10 again. So every time you multiply it times 10, you would move that decimal 1 place to the right. You got 2 10s there, so 2 places to the right gives you 7,865.9, and that is the end of our day 1. Day 2, I think we'll go a little quicker. All right, sorry about that. 32 minutes. Okay, let's move on to the next activity. Take care. Bye.
Hey, feeling good, like I should. When in dark, I walk around the neighborhood.